Now, let's discuss what is lazy propagation in segment trees. So when we discuss the updation part over here, I told you that we can do it in two ways. One will be having a linear time complexity, and the other one can be done in logarithmic time. So the linear time complexity will be just going to all the leaf nodes which are inside the given range of L and R, and then we'll be updating those values. Right now, what if I say I want to complete this in logarithmic time, but I want the correct answer or I want the correct updations. So we have the given array, and then I want to update the values in the range of 2 comma 4 by 2. So first I'll be just dividing it. So those steps are just the same. Now whenever there is a complete overlapping, then I will just modify that particular value and return back from there. I won't be going any step further whenever I have a complete overlapping. So I'll be just maintaining a variable called lazy, and if at all there is some complete overlapping, all the elements which lie within the this particular complete overlapping range should be updated. So that's what it means, right? So whenever I say complete overlapping, this S and E will be lying within the range of L and then R, which are to be updated, right? So if this is the case, then I can just modify this root node of this particular subtree, and all the values which come below it can be propagated later whenever they are in need. So in this case, if you want to update 2 and 4, I'll be dividing it into two parts. I'll be first dividing it into two parts such that the left sub array has the starting and ending as 2 and 0 and 2. Right hand subtree is 3 and 5. Now the values of L and then R are 2 comma 4. Let's look into the left subtree. So does the whole left subtree lie within this range? No, but there is some overlapping. So 0 to have some overlapping, right? So in that case, I'll divide further. So I'll be just dividing further into two parts. So this will be having 0 to 1 as the left part, and the right part will be having the index as 2. Now, if you see 0 to 1, 0 to 1 does not even lie or does not even overlap with the given values of L and then R, which means that I don't have to modify or update any values. So I'll be just returning back. Now for this particular 2, I'll be modifying it, right? So as this has some overlapping, and there is a complete overlapping if you see. So this is just 2 to 2, right? So 2 to 2 is complete overlapping with 2 comma 4. Hence, I'll be just modifying this particular value and returning back. Now, when we modify, I will take the length into consideration. So if it has only one element below it or only one leaf node, then I'll be adding only one time the updation value. So here the incremented value is 2, right? So we had to increment all the values by 2, right? So let it be as it is. Now let's come to the right hand subtree. Now here we can notice that the starting and ending is 3 comma 5, which is completely overlapping with the range of 2 comma 4. Now, what should be the updation value? So is it just 2, or should we be updating with taking the length into consideration? So the length over here is 3. So how can we get the length? So length is nothing but it will be E minus S plus 1. That will be the total length, right? So this starting and ending value, with it we can get how many leaf nodes are there in that particular subarray. So we have got the length, and this particular node, tree of index, should be updated with L times of the incremental value. That's correct, right? Because we are just incrementing all the values by 2, and there are only 3 elements over there. So if we update all the elements, then we'll be getting 3 times of 2. So instead of going to all the elements, I'll be just adding length times of increment value to the current node, and then I'll say that the left hand subtree, there is index 2 times of index, and then the right hand subtree ought to be lazily propagated. So I'll be just adding the value of increment over here. Lazy means that when we reach that particular element, there is when we reach this particular node, 7 comma 4 or 5, I have to lazily propagate at that time and then add these values. So that's what I'll be doing when we have complete overlapping. So this is in regards with the updation. Now let's quickly try to code this. So in the updation step, the first base case will be to look whether the given range lies within the updation range. So the range, the range of the subtree will be S to E, right? So we'll be checking whether this S to E lies within the range of L and R. So if it doesn't lie, then we'll be just returning back. Now, there's no overlapping, right? So this is the case where there is no overlapping. Now let's say I have complete overlapping. So what is the condition for complete overlapping? So if you remember the condition, this could be the condition for the complete overlapping. So in the case of complete overlapping, all I need to do is update the current index value and then make its two children as lazy propagated, right? So 2 times of index plus 1, 2 times of index, and then let's write subtree, which is 2 times of index plus 1. These two are to be lazily propagated. Now, what should we be adding to the current node? So, if you remember, I'll be adding length times the updation value. So, length will be e minus s plus 1, and then the incremented value is incur. So, this will be the updation value. Now, to its left hand subtree and right hand subtree, I just need to add these values. So that when I visit that particular node or that particular index, I'll be doing the same step. Right? I'll be updating those values. Now, when can we do these things? So we can only update when we are not at the leaf node. So if we're not at the leaf node, so the leaf node condition will be s equals to e. So if we're not at the leaf node, then update the lazy values for the right hand subtree and left hand subtree. That's it. So this will be the case of complete overlapping. Now the other case will be incomplete overlapping. There is partial overlapping. So in the case of partial overlapping, I'll be just dividing the array into two parts and then I'll be modifying it. Right. So that could be done. Also, if we have a complete overlapping, then after doing these updations, we'll be just returning back, right? So that we don't waste the time by diving deep into the subtrees. Now, do we need this case of s equals to e? So this is the case when we go to either of the leaf nodes, right? So this case can even be covered in the complete overlapping. So we can just take out this particular base case. So whenever we have a complete overlapping, we'll be just trying to update the first node and then we'll be making the children nodes as lazily propagated, right? Now, let's say we go to this particular node in the next call. So in the very next call, let's say we go to that particular node. Now, as these values are not equal to 0, which means that those values are to be updated, right? So when we enter this particular function, I'll first check whether the lacy of that particular index is not equal to 0. So if it's not equal to 0, then it says that that particular node needs to be updated. So I'll try to update it for node in the first place. So it should be updated with the value of its length times the incremented value. So length is e minus s plus 1 and with the value that is present in the lazy of index. Now for the children of this particular index, I'll be trying to make them as lazily propagated. So if s is not equals to e in this particular case, then I'll just repeat these two cases. So I had to update the lazy value for left subtree and right subtree. Now what should be the value that is going to be added? So I'll be just adding the same lazy value which we got for the parent, right? So if you notice over here, we are just updating the same value for the parent as well. And after this, the lazy value for the parent will be just 0, so that we don't update the value for the parent anymore. So at first, you're taking into consideration the case when lazy is not equals to 0, and after updating the current node, we are just checking for no overlappings, complete overlapping, and then these partial overlappings. So this is in regards with the updation. Now, even when we check for the querying part, so we just need to include this first case. That is, whenever the lazy value is not updated, we try to update it. So let's say we update some of the values, but the children are not updated, and we are making a query says that only some part of the update values are going to be included. Then those values have to be updated, right? So whenever we come to this particular query function, I'll check whether there is any lazy value which is yet to be updated. So we can even have this lazy value to be in negatives. So if you want to decrement the value, then this increment value will be in negative. So if you want to decrement all the values by 2, then I will just giving this increment value as -2, right? So I'm just checking whether the lazy value is not equal to 0, which means that it can either be negative or positive. So in that case, I'm updating the current element and I'm making its children as lazily updated, right? So we have to include this particular thing in both query range and then in update range. So let's say we want to update the values. So update range 1 comma 0 comma n minus 1. There is index, starting index, and then the ending value. And then we have to give the range which we have to update. Let's say we are updating from 2 to 4, and the incremental value is 2. So this is the transform array when we update all the values in the range of 2 comma 4 by 2, right? So I have made this into 7 9 and then 6. Now let's try to run the queries on this, right? Now let's try to give the same array which we have. So the array elements are 2 3 5 7 4 5. So this is segment tree after updation. Now let's say we want to get the sum in the range of 0 to 2. So we should be getting 12 as the answer. Yeah, so we are getting it. Now let's try for 2 to 5. So it's giving the answer as 27. So it says 27. So it's 16, 22, 27. So yeah, so this updation with lazy propagation is working fine. Now, if we check the time complexity for it, this will be running in logarithmic time. And why so? Because we are just going till the first part or first subarray where there's complete overlapping. So if there's complete overlapping, then we'll just update the first root node or root node of that particular subarray and we'll return back without visiting or diving deep to the leaf nodes. That's why the complexity will be nearly logarithmic. And when we want to visit that particular node, either in other range updates or in the querying part, then we'll be going to that particular node. That's why both this update range and then query range will be having a fair enough complexity of log of n. So with lazy propagation, we have reduced the time complexity of the updation from linear to something of logarithmic. So this is how lazy propagation is very important when we deal with segment trees. So these are all the important concepts with regards to segment tree, and I'll be attaching all these codes in the comment section. So with this, the basic concepts of segment trees are over, and in the next video, we'll start taking some good problems of the segment trees from CSES and other platforms like Spodge, Codeforces, and CodeChef. So that's all for this video, guys. I really hope that you enjoy the video and learn something uh, about the segment trees. And all the videos that I make about segment trees will be added in the playlist of segment trees and range-based queries. And if you haven't subscribed to this channel previously, please do subscribe so that you get the latest notifications. And that's all about it. So have a great day. And until next time, it's me soon signing off. Goodbye.